On April 10th, Apple and Google announced that they would be partnering together to develop contact tracing technology for the COVID-19 pandemic. In this blog post, they talk about how everyone is collaborating together to tackle this disease. And Apple and Google has taken it upon themselves to develop a technology solution around the problem known as contact tracing. The way that they propose to do that is through some application programming interfaces and possibly operating system level technology to assist in this contact tracing. What they say in this blog post is that they plan to implement this in 2 steps. The plan in May is that both Apple and Google will be releasing their APIs to enable interoperability between Android and iOS devices using apps provided by public health authorities. These public health authorities will be the ones implementing solutions using these APIs. They go on to say that in the coming months, both Apple and Google will be working to enable a broader Bluetooth-based contact tracing platform by building this functionality into the underlying platforms. This is a more robust solution than an API and would allow more individuals to participate if they choose to opt in, as well as enable interaction with broader ecosystems of apps and government health authorities. Once again, they emphasize on the privacy, transparency. They also look to openly publish information about our work for others to analyze. In conjunction with this blog post, they've also posted some preliminary API specifications. There's some links here. So we're just going to go ahead and have a look at that. This document here goes over the high-level architecture of how the system will work exactly. And again, they put the emphasis on privacy-safe contact tracing. They go off and start off to say that, explicit user consent is always required, and it doesn't collect any PII or user location data. The operation is that it collects a list of people you've been in contact with, and that never leaves your phone. People who test positive are not identified to other users, Google or Apple. It will be only used for contact tracing by public health authorities for COVID-19 pandemic management. And this is the interoperability that they wanted to touch on before. Since it's a collaboration between Apple and Google, the API is fully interoperable and it will work both on an Android and an iPhone. How this is really going to work. So we have 2 people, Alice and Bob. They meet each other for the first time and they have a 10-minute conversation. What happens during their conversation is their keys are exchanged via Bluetooth, and now Alice's phone has Bob's key without really knowing that that is Bob's key, and Bob now has Alice's key without really knowing that that is Alice's key. Now, a few days later, Bob tests positive for COVID-19 and enters the test results in an app from a public health authority. With Bob's consent, his phone uploads the last 14 days of keys for his broadcast beacons to the cloud. We go on to the Alice side of the equation. Alice continues her day unaware she had been near a potentially contagious person. But her phone in the background, the app, is periodically downloading all the broadcast beacon keys of everyone who has tested positive for COVID-19 in a region. So in other words, she's just getting downloads of all these keys, but she has no idea whose key is who, and that's the key part. The main part of the privacy application of this. So she downloads all the broadcast beacon keys of everyone who has tested positive for COVID-19 in her region. A match is found with Bob's anonymous identifier beacons. Alice's application only knows that she has a key of someone who tested positive. It doesn't know whose key it is. We only know there's Bob's because of the entire context that we have. From Alice's perspective, all she knows is she has been in contact with someone who has now tested positive for COVID-19 in the 14-day period. Now that we have got this match, the application will then go ahead and give Alice an alert via a notification on her phone that will say, "You've recently been exposed to someone who has tested positive for COVID-19. Now let's dig into the low-level specifications to see how this is really going to work according to Apple and Google. The contact detection service is the vehicle for implementing contact tracing and uses the Bluetooth Low Energy for proximity detection of nearby smartphones and for the data exchange mechanism. What they're trying to achieve here is by using Bluetooth as a 2-prong approach. Basically, the first prong is use Bluetooth to detect who is nearby, and 2, use it to exchange information that will allow that person to identify whether they've been in contact with someone who tests positive for the disease later. What's great about this is it means that we don't need to exchange any kind of location data other than the relative location of 2 individuals. It doesn't expose where any individuals were at any point in time, only their relationship to each other. So let's go through the quick definitions that they have here. Contact detection service, the BLE service for detecting device proximity. Tracing key, a key that is generated once per device. Daily tracing key, which is a key derived from the tracing key every 24 hours for privacy consideration. Diagnosis key, the subset of daily tracing keys which are uploaded when the device owner is diagnosed positive. Rolling proximity identifier, a privacy preserving identifier derived from the daily tracing key and sent in the Bluetooth advertisements. Changes every 15 minutes to prevent wireless tracking of the device. So the first section, we have contact detection service. So the contact detection is a BLE service. This is basically just the implementation details. The contact detection service payload shall be ordered as shown below and shall not include other data types. The contact detection service payload has three sections. It has a flag section. The LE general discoverable mode bit 1 shall be set to 1. So in other words, it's in discoverable mode. The 16-bit service UUID, the UUID is 0xFD6F and shall precede the service data section. Then the remaining 16-bit UUID section is the content of service data payload, which shall be a 128-bit rolling proximity identifier. The gist of it is this is the payload for advertising on Bluetooth. So the first section is just saying that it is in general discoverable mode. The middle section is identifying what service it is. In other words, this is the identifier that they've allocated for the contact detection service. And this will be the same for anyone implementing this service. And then we have the service data. So this is just data that you can transfer. And in this case, it has the rolling proximity identifier. If we go back to the definition, we can see that the rolling proximity identifier is an identifier that changes every 15 minutes. So by having this rolling proximity identifier, it means that every 15 minutes, your advertisement payload is exactly the same. So for that 15-minute duration, you're advertising out to the world. What someone can do during that 15 minutes is listen to those payloads and see where you are and where you're going. Benefit of changing it is a person who is listening every 15 minutes, they have no idea whether you are the same person or a new person coming in to their sniffing device. Now, we can look at the actual advertising behavior and the advertising flows. This is how your phone will behave in advertisement mode for the contact detection service. So the advertisements are to be non-connectable, undirected. Basically, the advertisement cannot result in a connection to the device. It's a broadcast out into the world. Anyone who is in range of your Bluetooth device and has capability of reading that Bluetooth signal can read your advertisement, but they cannot use it to then connect to your device. Then they go on to say that on platforms supporting Bluetooth random private address with randomized rotation timeout interval, the advertised address rotation period shall be a random value greater than 10 and less than 20 minutes. The advertiser address and rolling proximity identifier shall be changed synchronously, so address and rolling proximity identifier cannot be linked. What that means is that every time your address or your rolling proximity identifier are changed, so will the other component of that. So that way you don't have crossover where your address is 1 and then it's 2, but your rolling proximity identifier is the same, so then someone can link those addresses together. And then they can actually discover your new rolling proximity identifier when it changes. A separate advertising instance should be used if hardware allows to provide advertising reliability and flexibility in choosing optimal interval. The advertising interval is subject to change, but is currently recommended to be 200-270 milliseconds. Now we can look at the advertising flow. So this is a flow diagram of how the advertising sequence of the contact tracing service will work. This is the Bluetooth advertising mode for this service. So how does it start? We're in the application, which is the health authorities application that we have. And then we start off with the CT state set request. And what this does is it generates the tracing key if it doesn't exist and saves it to our disk. Then we can derive the daily key from the tracing key, which then we can derive the rolling proximity identifier from the daily key. We then get that back. Then we can start advertising. And this is the other side. This is someone else's phone. The Bluetooth module detects this advertisement and saves the rolling proximity identifier. After 15 minutes, we derive a new rolling proximity identifier on our side, and then we have an advertisement again. And again, the other person saves the rolling proximity identifier. Then after 24 hours, we derive a new daily key from the tracing key, and the advertisement flow repeats. Now we can look at the scanning behavior. Now the scanning behavior is actually retrieving someone advertising this rolling proximity identifier to you. Any discovered contact detection service advertisements will be kept onto the device that is scanning, and the scan results will be timestamped and have the signal strength captured per advertisement. Now, keep in mind that the scanning interval and window shall have sufficient coverage to discover nearby contact detection service advertisers within 5 minutes. The window will be small enough that every 5 minutes we will retrieve at least one rolling key. Obviously, there's some power considerations. We don't want to be scanning too much that we drain the battery completely. That has to be part of the engineering consideration. We'll quickly look at the scanning flow because it's interesting to understand how this is really working. We have the app, and we make a request to scan for contact detection service UUID. We receive advertisements from anyone, and we save the rolling proximity identifier. We also periodically fetch our diagnosis key, and we get the diagnosis keys from the cloud. This is basically all the keys that have had a positive diagnosis of COVID-19. We resolve the diagnosis keys against all the rolling proximity identifiers. Then we do resolution using the crypto module. We decide whether it's a match, and we also know exactly how long you were exposed to a particular contact based on how many rolling key proximity identifiers you have of them saved to your phone. So the algorithm will assess the risk based on the exposure duration, possibly even how close you were based on the signal strength. Then we'll get the information that we've been in proximity to someone who's been diagnosed. So this is the look at the cryptography specification of this contact tracing API. So there's some external functions. We have concatenation. They use the symbol double pipe. HKDF function as defined by the specification using the SHA-256 hash function. HMAC, another standard function. And truncation is just truncating some data. Day number provides a number for each 24-hour window. Essentially, it's just the number of days since the epoch. We also have a time interval number, which provides a number for each 10-minute window in a 24-hour window. CRNG is a cryptographic random number generator. This is the key schedule for contact tracing. We have the tracing key, which is unique per user. This is generated the first time you open the application. Then we derive the daily tracing key from the tracing key, and this is generated once per day. And we use the MAC algorithm to generate a rolling proximity identifier, which is one per broadcasting rotation interval. What this means is, going back from before, every 15 or so minutes, a new one of these will be generated using the MAC algorithm based on the daily tracing key for that day. The tracing key is generated when contact tracing is enabled on the device and is securely stored on the device. It uses the cryptographic random number generator that we saw before with an input of 32, specifying the byte length. No one knows the tracing key except the application when it's deriving the daily tracing key. Now the daily tracing key. A daily tracing key is generated for every 24-hour window where the protocol is advertising. From the tracing key, we derive a 16-byte tracing key in the following way. It uses the HKDF algorithm where we're given the original tracing key and the UTF-8 of CTDTK concatenated with DI, where DI is the day number for the 24-hour window the broadcast is in. It goes on to say that upon a user testing positive, the daily tracing keys for days where the user could have been affected are derived on the device from the tracing key. We refer to that subset of keys as the diagnosis keys. What's important here is that your daily tracing key is never saved on your device. It's generated every time we need it to generate the rolling proximity identifier and when we need to upload the diagnosis keys to the server. But the daily tracing keys are not saved on your system because they can be re-derived from your tracing key and knowing which day you were infected. Again, if the user remains healthy and never tests positive, these daily tracing keys will never leave the device. The use of 16-byte keys allows to limit the server and device requirements for the transfer and storage of the diagnosis keys while preserving low false positive probabilities. What they mean by false positive is if that, given the 16-byte length, there is always a possibility that two people share the same daily tracing key. The best way to look at that is through an example. Let's take 3 people, Alice, Bob, and Jerry. Alice and Jerry meet up one day and they are in contact for about 10 minutes. Therefore, they transmit their rolling proximity identifiers to each other twice. 5 days later, Bob, who Alice and Jerry have never met before, contracts COVID-19 and enters into the application that he is infectious. However, Jerry and Bob had the same daily tracing key by chance. What happens now is that Bob uploads all his daily tracing keys in the last 14 days to the server and marks these as diagnosis keys. Alice's phone then downloads all these keys and identifies that she has 2 rolling proximity identifiers generated by that daily tracing key. To her application, it seems like Jerry was infectious. In this case, this is a false positive because actually Jerry never had the disease and Alice was never in contact with Bob, who was the one that had the disease. But because Jerry and Bob shared the same daily tracing key in the 14-day period, it looks to Alice as if she was in contact with someone with the disease. By having a low false positive probability, we reduce the risk of this scenario becoming a reality. The rolling proximity identifier is a privacy-preserving identifier that is sent in Bluetooth advertisements, which we saw before from the Bluetooth specification. Each time the Bluetooth MAC address changes, we derive a new rolling proximity identifier. And it's derived using the HMAC function, using your daily key, followed by the text CT RPI concatenated with TIN-J, where TIN-J is the time interval number for the time at which the Bluetooth Low Energy MAC address changes, and 16 being what we want to truncate the HMAC to, giving a rolling proximity identifier of 16 bytes. Matching values from users tested positive. This is the interesting part. This is how the application determines whether you have come across someone who has tested positive. Upon a positive test of a user for COVID-19, the diagnosis keys and associated day numbers are uploaded to the diagnosis server. A diagnosis server is a server that aggregates the diagnosis keys from the users who tested positive and distributes them to all the user clients who are using contact tracing. In order to identify any exposures, each client frequently fetches a list of diagnosis keys. Since diagnosis keys are sets of daily tracing keys with their associated day numbers, each of the clients are able to rederive the sequence of rolling proximity identifiers that were advertised over Bluetooth for the user who tested positive. In order to do so, they use each of the diagnosis keys with the function defined to derive the rolling proximity identifier. For each of the derived identifiers, they match it against the sequence they have found through Bluetooth scanning. Additional validation can be used to confirm that the advertising happened in a time window comparable to the one expected based on the time interval number. Matches must stay local to the device and not revealed to the diagnosis server. What this really means is that you will receive the daily tracing key for everyone who has been diagnosed, and they also have their associated day numbers with them. Therefore, we are able to derive the time interval number throughout the entire day using the algorithm for time interval number. Now let's look at the privacy considerations. The key schedule is fixed and defined by operating system components, preventing applications from including static or predictable information that could be used for tracking. In other words, the API cannot be manipulated to add additional information. The entire API takes care of how the keys are derived. A user's rolling proximity identifiers cannot be correlated without having the daily tracing key. This reduces the risk of privacy loss from advertising them. Now this makes sense because your proximity identifier changes every 15 minutes on average. From someone observing this, when yours changes, it looks like you're just a new user. Without having the daily tracing key, there is no way to know that 2 rolling proximity identifiers came from the same key. Since they were generated using a cryptographic algorithm, we would need the daily tracing key as well as the day number to know how to regenerate the rolling proximity identifiers and then correlate them together. Now obviously this correlation with the daily tracing key is important because when we get the diagnosis, we can figure out how long we were exposed to a particular contact without knowing who that contact was. A server operator implementing this protocol does not learn who users have been in proximity with or user location unless it also has the unlikely capability to scan advertisements from users who recently reported diagnosis keys. An operator of the diagnosis server has no way to know whose key is who. Without the release of the daily tracing keys, it is not computationally feasible for an attacker to find a collision on a rolling proximity identifier. This prevents a wide range of replay and impersonation attacks. When reporting diagnosis keys, the correlation of rolling proximity identifiers by others is limited to 24-hour periods due to the use of daily tracing keys. The server must not retain metadata from clients uploading diagnosis keys after including them into the aggregated list of diagnosis keys per day. What this really means is that someone retrieving daily tracing keys are able to correlate all the rolling proximity identifiers for a single 24-hour period, but they're not able to know that the new daily tracing key for a particular person for the next day is the same person. The keys are distinct for every 24-hour period, and each rolling proximity identifier is generated based on the daily tracing key. That means for each day, it looks like a daily tracing key is a new person. There is no way to link two tracing keys together. So that was a bit of a breakdown of the technical specifications of this contact tracing that Apple and Google are proposing as a solution to COVID-19. Clearly, this specification is very early days, although looking through it now, it seems that they've considered quite a few potential scenarios and they've come up with solutions to those problems, specifically in the privacy and security space. It'll be interesting to see where they go with this from now, and who knows, maybe it'll be an effective solution to contact tracing.